Yeah. So in the conductors, basically you can tune the resistivity and this thing. So this was the first module, and then second was the classical versus quantum. So in this actually, so when describing like when finding out the microscopic details of the crystals in solids or those things, the dimensions are of the order of few angstrom. So the length scales are tens of angstrom, or atomic dimensions are in the order of angstrom. The distance between the atoms in a solid, or so at these dimensions actually. So the like distances are such that like your normal and classical pictures does not hold, and even the particles behave like dual natures, like electrons and other subatomic particles. So you can't really have like the electrons has a mass 9.1 into 10 power minus 31 kg. So it has a very less mass. So it has the energy is of the order of very less scale. So you can't describe the whole picture by just by the classical mechanics. So basically, to categorize this categorization, insulator, semiconductor, and conductors is not possible without dealing with the quantum mechanics or quantum nature of the particles or electrons per se. So that is important. And for describing the solids, we can roughly assume that the uh, yeah, sorry. Sorry, I lost the connection in between. So, yeah. So, uh, yeah. So, yeah. So now, so to describe a crystal, basically, you need to consider a periodic arrangement of atoms, and that potential has a Coulombic potential. So it has 1 by r square dependence or 1 by r dependence potential, and electric field has a 1 by r square dependence. So this potential you can like the Coulombic potential you can so this periodic potential actually is very difficult to solve if you take, let's say, a larger number of atoms. So basically you can take the approximations actually. So considering that this has a square potential or rectangular potential, rectangular periodic potential. So that is the chronic penny model. So by considering this periodic potential, you can describe the like how the wave function will evolve for a group of atoms arranged in periodically. If your the atoms has the space periodicity, so how you can how the energy versus wave number or k ek relation changes. So as described in the class, the for free electrons the ek diagram is basically just the parabolic. So it just follow E is h bar square k square by 2m. If you need to solve the Schrodinger equation for a free electron, so you can solve by just by taking the zero potential. But if you discuss the if you consider the electron in a periodic potential, then this at the periodic intervals of the k values, there is there is a discontinuity because of that. So that you need to consider. So now because of that, that band forms actually, because this discontinuity arrives here, and those these gaps are basically discontinuities coming because of the periodic potential, and you are considering interaction within the wave function. So this over the course we will I will summarize the session in the next, and let's just try to discuss the problem. If you have any other doubt, then you can ask, or otherwise I can carry on. Is there any doubt? Okay. Okay. This is basically some practice problems based on the past question history. So this may be helpful in solving your current assignment based on the content covered in the lecture slides. So these may be like the actual assignment may be little bit different compared to this one. So you can refer to this, and this may be a test bed for your exams and entrance papers. So the first problems talks about the silicon has a diamond cubic structure. So you might have heard like what this diamond cubic means. So the diamond cubic so let me just give a outline out what this diamond cubic means. So what is diamond is doing in the silicon actually. So basically so in the carbon, if you see the different allotrop or different phases, so you see the diamond and two very well known phases are like which you can see like which you use for very child, like two form of carbon you have seen. I think everyone have seen at least one. I have everyone has seen that graphite, which you know from from childhood. So the graphite is a different form of a form of carbon. It will very thin sheet of the of the carbon atoms, and hexagonally they have hexagonal close packing structures, and this these form the covalent bond within the plane, and the van der Waals bond across the plane. So there is considerable large interest in this kind of uh, structures, like the from very childhood we have seen that graphite kind of structures which we use in our pencils for writing from childhood. and then like the recent interest, if you take few layer or few atom like few layers or single layer of these graphite, then it will become graphene. And there is a lot of interest in like some transport and devices perspective in last decade or so. So this discovery was awarded Nobel Prize, I think, around 2004 or 7 something. So yeah, so this has attracted a so this is one form of carbon. Other very well known form you might have seen, at least heard the name, is diamond. So which like I think most of the people heard about this diamond. So in the diamond, basically the carbon is bonding to the nearest four atoms by the covalent bond. So and this bond has the angle 109.8 degree spacing, angle spacing between each carbon bond. And if this structure is repeated, then this forms the diamond cubic lattice. So what is the meaning of diamond, and this the what is the meaning of cubic? So this basically like if you take a diamond, so to form the diamond lattice, so and so let me draw this crystal. So let me draw the crystal approximately. So the diamond cubic. So to make the crystal, to make the crystal, first you should have the symmetry actually. So uh, for the symmetry, basically like the symmetry is the crystals in the crystal, a few group of atoms are repeated in the space h by z direction. So that is not the basis unit or primitive cells. You have studied in the your 12th class or those school level like post intermediate level, school level, the different phases of solid state actually. So you might have heard like the simple cubic structures and base centered cubic structures, f phase centered cubic structures. So the diamond basically so for diamond cubic structure, the lattice is lattice is face center cubic. So that means the each atom can be at the face of each face of the this, as well as at the corner of the crystal. So here this diamond, but the diamond cubic structure is different. So so to make a crystal, first you should know the symmetry properties, and then basically you should know like then to make the crystal, basically you need to put the actual atom. So the diamond cubic crystal forms when uh, when you put at each so diamond cubic crystal forms when at the each lattice side. So whatever this where this sides of like the where the FCC points are there, those are known as a lattice side. So in a FCC lattice, if you put two atoms at each side with the XYZ spacing at A by 4, A by 4, and A by 4. So where A is the A is your side length. A is the one of the side of your cubic FCC lattice structure. So basically, if you repeat this arrangement, if you put this two carbon carbon at each point, even here also you put one carbon carbon, here also you put same carbon carbon, then you will realize you will form a this kind of geometry that the each carbon will bond to the nearest four atoms, and that is that will be bonded as tetrahedral covalent bond. this structure is known as a diamond cubic. But since silicon is also group 4 element, it just lie in the periodic table, it just lie just below to the carbon. So it also has kind of similar property. So this also follows the diamond cubic lattice structure. So basically, so in the FCC lattice, in the FCC lattice, if you at each FCC site, so this at the corner and at the each face is your FCC site. So basically, if you put this two silicon atom at each at this distance a by 4, a by 4, a by 4, then basically you will come around the diamond cubic structure. So so to calculate the density of the diamond cubic structure, so basically you need to calculate how many number of atoms. So in this problem, basically in the diamond cubic lattice structure with a so is this clear? Is I am going a little bit overboard or something? Is it clear? Okay, so yeah. So so basically to calculate the density, so basically you need to calculate within the you need to calculate in the atoms per centimeter cube. So basically, the crystal is just repetition of this. So if you calculate the total number of atoms in this and divide it by the volume, then you will get basically like per unit volume how much is your how many number of atoms you have. And since the crystal is just repetition of this, then you basically the density will be the same. It can be assumed as a uniform density of that. So let's count the atom. So in this cubic or FCC structures, so there are there are 8 corner atom. So this corner atoms will be basically if you extend this if you extend this then you will see that in the in the in the plane of this this is shared by 4 unit cell. This each corner in this plane is shared by the 4 unit cell. And at this vertical plane, at this plane, if I can draw this plane, so this if you extend, this if you can extend, and this if you can extend, then this plane also it is shared by the 4 unit cell. So basically each corner is shared by the 8 unit cell. So the contribution in this particular unit cell of the carbon atoms, and total 8 carbon atoms are there. So total number of atoms in this unit cell is basically uh, it is total number of atoms is 1 by 8 contribution multiplied by 8 atoms. Plus these are the edge one. So and these phase atoms are half shared. So this phase atoms is just shared by the next nearest neighbor unit cell because this is repeated. So there are total 6 phases. So half multiplied by 6 are your phase center at each phase center of the cubic cell, and then there are inside this 2 atom here, plus 4 atoms inside the cell. So because of that, plus 4 atoms. So the total atoms in this unit cell are 1 plus 3 plus 4 is around 8 atoms per cell. So if we know the covalent bond and and we know the lattice constant. So the lattice constant is given. So we can calculate the volume of this cell. And if we calculate the volume of this cell, then we can calculate what is the density of atoms. So this atoms, this has the 8 atom per unit cell. If we calculate, if we divide the volume of this cell, then we can get how many number of atoms per unit cells are there. So the atoms is just lattice constant cube, because this is so this is the lattice constant and this is given. So the density is 8 atoms divided by uh, 5.3 angstrom, 5.43 angstrom uh, cube. So if you convert into the centimeter, so the density throughout this course will be described in the centimeter. So it will be uh, around 1.126 point something into 10 power minus. So it is 10 power minus uh, minus 8 centimeter cube. So if you calculate this by calculator, so this 8, it will become 3. So it will become, the number will come around 5 into 5 into 10 power 22 atoms per centimeter cube. So please keep in mind this number. So this number will be like you can compare when we will do the doping. So what fraction of this we can achieve the doping. So is that clear? Anyone? You can just type in the chat box. Any doubt or any confusion? Huh. Which one? This problem. Okay. Your voice is bit is unclear. Can you type? Okay. 1 by. Okay. Hmm. 6. Yeah. And then, so where your confusion is, why this half into 6 tons is coming? Yeah, yeah, you are audible. Just speak. Yeah. Hello, hello. Yeah. 8. How it's this is coming? Hello. Uh, okay. Banma. Okay. Let me. So see. Let me draw it bit clearly. So let me bit put in more effort. Let me draw the crystal. Let's focus on the edge atom actually. So I don't know. Network is quite stable. Yeah. So let's just focus on the this crystal actually. So yeah, I am just extending this crystal to the other direction also. So 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 yeah. So now let's say this is one of the unit cell. So this is one of the unit cell, and this unit cell will be repeated actually. In crystal, it will be repeated. So if I make the other unit cell similar, like there will be unit cell just near to this. So just wait a minute. Uh, yeah, just let me just draw it. Yeah. So see, like this, if I extend this unit cell, so this in the plane, this atom is shared by this unit cell, this unit cell, this unit cell, this unit cell in the plane. So this plane, if you see, so this plane, it is shared by this four unit cell. Is this clear? Hello, hello, hello. Yeah. So is it clear? Hello. Okay. So now in this plane, this is clear. So now in this plane, this is shared by four unit cell. Now the because the structure is repeated in 3D also. So on the top also, one unit cell will be on the top of this unit cell. So if you draw that unit cell, so then it will be on the top one also. Like one is this plane. On the top one also, it is shared by four unit cells. Similar on the top, if you can imagine. So this is now this one atom is shared by eight unit cells. Is that clear? Maybe like my drawing is a bit bad, so let me just draw it with a different color. So let me take this green color. So this so basically this so this is one of the unit cell on the top of that unit cell, right? And this you can extend this side also, and similar you can extend this. So this yes. So this also you can extend. So this, if you draw this crystal, so uh, just wait. So if you draw this crystal, so yeah, so this also you can extend. So this will be this will be one of the crystal cell, and the same the back side also you will have this unit cell actually. So this unit cell. So you can see like this 1, 2, 3, 4. So this is shared by the four unit cell on the top also. 1, 2, 3, 4. So the four nearest neighbor cubic cell, it will be sharing. So that's why this contribution is four at the bottom, four at the top. So total it will be shared by eight unit cell. So is it clear? Okay. So now is it clear? And this how this half into six is coming? Yeah. So basically this face centered one, because this is at the center of the unit cell. So only the nearest neighbor of the unit cell it will be get shared. So this atom will share to this unit cell at the side only. Other unit cell it will not get shared actually. So that's why this is shared in two unit cell only. So that's why the total contribution in this particular unit cell is half. And this the covalent bond, these atoms come inside actually. So if you place and two atom will come here and two atom will come here. So these four atom will be no, I'll make a mistake. Yeah. So just not this atom. Yeah. So these four atoms will be completely inside, if you can see, like because this is diamond cubic structure. So these four atoms we need to take whole contribution actually. Is that clear? So this whatever you have studied in your 12th class, you might have studied this FCC structure. But the actual crystal, this is the basis for the this is the lattice. Plus, you need to put actual atom. So, like some analogy, you can say, suppose you want to make a garland out of beads. So, one way is like you take let's say blue color beads. So, you want to make repeated blue color bead that you can take as a garland. So, each bead position is the lattice point actually. Now you can make a different design of garland similar way. So you can make like this also. So let's say you take the atoms. Now instead of taking blue bead, now you take alternate combination of blue and red, blue and green. So yeah. So if you take this green bead in between, you add. So this will look like a different design. So you can say, so this structure of atoms, this structure of beads in your garland is getting repeated. Actually, that's why this is periodic. So at each lattice point, you can assume that you are putting two beads actually. So this is the same thing actually. So at each face centered cubic lattice point, you are putting two carbon atoms. Similarly, like there are other kind of structures like cadmium, like some you can put a different kind of uh, atoms like gallium nitride. One kind of semiconductor is there. So basically, you put you put gallium and at one lattice point, nitrogen at other lattice point. So that is different kind of geometries kind of. Is that like basic overview? Is it clear? Is there any confusion? No. Yeah. So this like putting this having this crystal structure is known as the basis. So this is bit advanced terminology, but this is like more you can like go through some solid state book. You won't find much in semiconductor device book, but other higher level solid state physics book you can find actually. So this basis plus motive. So whatever, so the basic structure of your garland is your basis plus whatever the atoms you are putting, that is whatever the beads you are putting, that is your motive. So basis plus motive forms your crystal. Okay, so is there any confusion or should we move to next problem? Okay, so let's move to next problem. Given the uncertainty in position of electron, so basically this problem deals with the uncertainty principle. So basically, like Heisenberg uncertainty principle, Heisenberg's Heisenberg's uncertainty principle. So so what did they say? Like at a particular instant of time, the uh, uncertainty in position delta x is basically how much uncertain your position is, and uncertainty is p is must be greater than h bar by 2 pi. So this this says, so basically, like if you go in some advanced text, this is like some commuting variables and those things, like position and momentums are not non-commuting variables. In the quantum mechanics, basically, if two variables are not non-commuting, so you can't observe them simultaneously at the very high precision. So if you have precision is very in one, then you need to compromise the precision in other. So basically, if you have, so if we this principle, if you take delta p must be greater than equals to h bar by 2 pi delta x. So if you have particular precision, so delta p, so uncertainty in position is inversely related to uncertainty in position. So basically, if you know the position very precisely, then you don't know what is the momentum, what is the uncertainty in momentum, and vice versa. So if you know the momentum precisely, then you don't know the position actually. So this is the uncertainty principle. So let's apply this for a electron. So given the uncertainty in the position of an electron at delta x equals to 8 angstrom, it's giving, so you can write 8 into 10 power minus 8 meter, or minus 10 meter, or 8 into 10 power minus 7, 10 to the power minus 8 centimeter. If the nominal value of momentum is given as this 1.2 into 10 power 10 to the power minus 23, determine the corresponding uncertainty in kinetic energy. So basically, for free electron, the kinetic energy is given is the because it does not like have it is not under the influence of any electrostatic potential or any potential. So it will has only kinetic energy. It will not have any potential energy. So the whole energy is basically p square by 2m, or half of mv square is your kinetic energy. And if you take derivative with respect to energy, so delta E by delta P, if you take so dE by dP, if you take, then you need to take derivative with respect to P. So this will become 2P by 2M multiplied by dP by dP. So this will two will get cancelled, and this then you can consider like this p by m times the dp. So this is the uncertainty in your momentum, and this is the uncertainty in your energy. And this from here uncertainty relation from the momentum and position, you know that this must be greater than equals to p by m times delta p is must be greater than equals to h bar by h, so it is h bar by 2 pi into delta x. So the t uncertainty in energy must be greater than equals to p h bar by m times 2 pi delta x. So basically, the delta x is provided, nominal momentum is provided, mass of free electrons we know, so that is 9.1 into 10 power minus 31 kg, and momentum we have given, momentum is given as 1.2 into 10 to the power minus 23. So this is 1.2 into 10 minus 23, and the h bar is h bar value is 1.05 into 10 power minus 34. So this is 1.05 into 10 power minus 34 joule. So that you can consider calculate the uncertainty in joule, and like this, if you put a Planck constant value in joule second, then you will get uncertainty in joules, and you to get in electron volt you need to divide by 1.6 into 10 power minus 19 electron volt, because 1 joule correspond to 1.6 into 10 to the power 19 electron. So that you can convert to the electron volt. So you will get around 5.48, which is the B option, electron volt, for the answer. So exact scale you calculate and let me know if you have any doubt in the next class, or you if you don't, sure answer is not matching with mine, so that please let me know. Is that clear? Okay. uh, yeah, is there any confusion? Okay, fine. Yeah, thanks. Okay, so let's start with the next problem. So electron and the photons have the same energy. At what value of photon energy, the wavelength of the photon is 10 times of that of electron. So lambda p is given as 10 times of lambda e. So the photon energy is basically given by photons has zero rest mass. So basically, so you can calculate the energy as h bar omega, or h c by lambda, or c by lambda you can take as new frequency of the uh, of the of your electromagnetic waves, or which correspond to that photons, that you can calculate with the wavelength you are giving. Then you basically c by lambda is your frequency. So from that you can calculate energy of the photon, and the energy of electron, this is matter. So the energy of electron is given as p square by 2m, free electron we are talking about. And with the de Broglie hypothesis, de Broglie gives a relation that at microscopic scale, even the matter waves can behave like wave nature actually. So at the micro scale, like subatomic particles like electron, proton, neutron, they can behave like a particle, also like a wave actually. So you can associate the wavelength corresponding to that, and that wavelength is given as a de Broglie wavelength actually. So if you divide by momentum of electron or momentum of particle by the if you divide Planck constant by momentum of particle, then you will reach at this. Then you can calculate the wavelength of the matter wave actually. So he hypothesized that the matter and wave is dual character. So is depending on which application you are considering, it can be considered a particle or wave actually. So because like this, people observe different kind of, like people measured spectra of hydrogen. So what happened, that spectra does not have any continuous thing actually, that has discrete spectrum line at this point. So that can be explained by the considering the particle nature of the electrons also. But then there was a different experiment, like Young's double slit experiment. So basically, what people did like this Young double slit experiment with electrons. People try to do. So what they see, if the electron is particle, so basically then it can't have any interference and those patterns which wave, like Young double slit experiment, which you have seen in your 12th class, or undergraduate you have seen. So basically wave, this the interference will occur actually. So this interference pattern will form. But people did experiment with the electrons also, but people find the that interference occurs for electron also. So this like if you consider the particle nature here, then it can reach the particle can at a time can go to one of the slide, and when this goes to only one of the slit, then it can't have interference pattern actually. So to explain this interference pattern, only the wave nature of electron can explain this interference pattern. So that's why people consider that the matter can behave like a wave and uh, not a particle. So like the uh, like for example, in the macroscopic object which you see in daily around, that picture holds true actually. You can represent as a wave, but the wavelength of that wave will become very large actually. So the electrons, so the wavelength of electron, if you consider, that comes in the nanometer range, and those kind of range. But if you consider, if you take larger objects, if you calculate the momentum, and if you divide by the Planck constant, you will see that they have very larger wavelength actually. So that, like if your wavelength is larger compared to your size of the particle, so if your matter wavelength is very large compared to the size of the particle, then you can consider classical picture very accurate. But once they start to become near about this, like when the size of the particle or the scale of the distance which you are considering is nearly equals to the wavelength, matter wavelength, de Broglie wavelength of the object, then you need to consider the wave picture also to explain all the phenomena. Like some phenomena you can just explain with the particle picture, but otherwise you need to take the phenomena. So, like if you calculate the momentum by de Broglie wavelength, so then P is basically h bar by lambda e. So the energy of electron you can calculate. So this will become h bar square by 2m lambda e square, and then this you can calculate equate to the photon energy. So that you can so if you equate to the photon energy, that is h c by lambda photon, and that is h bar square. So this is h bar square divided by 2 me 2 m mass of electron time lambda e square. So this h you can like h bar you can replace h over 2 pi. So this is reduced time constant. Then you can calculate basically 10, and your lambda p is given as the uh, so yeah, so basically you need to take ratio of these two energies. So let's not equate it. So basically, if you can take the ratio of these two energies, so then you can calculate. So the just wait. Yeah. So then you need to calculate. So it's given. Just wait. The electron and photon has the same energy, and at what point of photon energy the just wait. Okay, yeah, so basically so this equation we need to at same energy we need to equate, and then from here we can calculate the wavelength actually. So so this is uh, hc by lambda p is given as 10 times lambda e electron wavelength, h bar square by 2 me lambda e square. So this square, then this will get cancelled. So lambda e you will get lambda e will you will get 10 times h bar square by 2 me into hc. So hc h bar you can replace by 10 times h over 2 pi whole square, or you can take h bar here, or you can replace h over 2 pi, and then you can 2 me hc. So you, this h will get cancelled with this h. So what you will remaining, so this 10 h bar divide by 2 pi multiply by 2 me times c. So this is your lambda e. So from there, c, you know this the velocity of light 3 into 10 power 8, and this me you know 9.1 into 10 power minus 31, and h bar you know like 1.6 into 10 power minus or 1.05 into 10 power minus 31 34 minus 34, and then like the 2 pi and others are those constant. So from there you will get lambda e. From that you can calculate lambda p is just 10 times of lambda e, and just to calculate uh, energy of photon, you need to put lambda p here actually. So basically you need to put lambda hc by lambda p. So from there you can calculate lambda p, and if you put with the exact number, you will reach out the answer will be around the 10.5 kilo 10.25 kilo electron volt. So it is, see, like this is like very high energy actually. So the like room temperature thermal energy is around 25 milli electron volt inside, and this is kilo electron volt of photon energy is required to have the uh, same energy that of a electron actually. So that's why the matter waves are quite higher in energy, and like those yeah. So is this clear? Is there any doubt you can ask? Okay, so if there is no doubt, let's just move further. Okay, so let's just move to next problem. So so the so the next problem talks about consider the system with the 10 to the power 19 one electron atom at equilibrium atomic spacing. Due to interatomic interaction, the energy level of individual atom hybridize. So basically, if you keep all atom very far away so that their interaction is not there, so all will have same energy. But you, as you bring down closer and closer atoms, then this their wave function will start, wave function of the last uh, outer cell electron will start overlapping actually. Those will have interaction that will lead to splitting, or splitting of the energy level. So if you keep all the electron away at different very far away distance, then all will have same level. But as you keep decreasing the distance, this level will get split, and this will this degeneracy will get broken, and you have a distribution of levels actually. So if you consider atoms as equally spaced, then you can assume this like this distribution is uniform. So basically in this the total energy band is 1 electron volt, and there are the number of level will be same as the number of atoms. So you can calculate how many the what will be the energy spacing will be of the order of. So the delta spacing will be of the order of the total spacing 1 electron volt divided by total number of atom 10 to the power 19, which will be equals to, so the energy will be equals to 10 to the power minus 19 electron volt. So so the this fine energy will be there. And because like now like this because uh, this so which of the following statement is true? The energy band represents the forbidden gap of the energy band diagram. No, the forbidden energy gap does not come because of uh, that comes because of this, but like this these levels a particular level of single electron become non-degenerate actually. So the band gap will form as the when the different core electron interact with the outer cell electrons, and those redistribution happen, then it will be a band gap. Second option is the energy and band gap can be considered with quasi-continuous due to the small spacing between the energy level. So this you can see like this spacing is 10 to the power minus 19 electron volt. So this is quite a smaller electron energy level. So you can compare that energy level to room temperature thermal energy level. So that is 25 milli electron volt. That is 25 times 10 to the power minus 3 electron volts, and this energy separation is 10 to the power minus 19 electron volt. So that is 10 to the power 15 order of difference actually. So with this energy scale, you can assume like the thermal energy is enough to have the uniform distribution among these many levels. So you can kind of assume that the electron will form a quasi-continuous band between the energy level. The fourth option is energy band cannot be considered to be quasi-continuous due to the small spacing between the energy level. No, uh, this is wrong statement. Because of the small energy only, you can consider the quasi-continuous, because within this level, the thermal, like your environment is putting energy into the electron, so it can jump uh, to the level because it has very small energy spacing, and it can move around in different energy level. So that you can on an average you can have that electron will have equal probability of finding in one of the energy level. The discrete energy of level in the band is important in yeah, it is important, but this is not the correct answer. So the correct answer is B1. So you can assume this as a quasi-continuous level. So is there any confusion in this? Is it clear? Okay, so if there are no doubt, then I assume it's clear. So calculate the change in kinetic energy of electron traveling with the velocity uh, and change by small amount increase by 100 centimeter. So E is basically half of LB square or P square by 2m. So basically, so delta E you by small change in delta V you can calculate with respect to velocity. So half m. If you take derivative, this will become 2v. So this will become cancel. So delta E will become uh, mv times delta v. So then you can calculate what is the mass is 9.1 into 10 power minus 31 kg. Velocity is 10 power 17, 10 power 7 centimeter per second, and delta v is 100 centimeter per second. So this you can calculate. So this so basically this in, if you consider in like SI unit, so 9.1 into 10 power minus 31, and you can consider into meter. So this is you can consider 10 power 5 meter, and this will become 1 meter per second, 1 meter, and then you can divide by 1.6 into 10 power minus 19, then this will become electron volt. So the final answer you will get around 5.6 into 10 power minus 17 minus 7 electron volt. See like this. The 10 to the power minus 7 electron volt increase, 10 to the power 7 velocity will lead to this much change, and your spacing between the energy levels in the above part were quite smaller compared to this change. Then you can assume like the electron can be any of those equally spaced layer. So is there any confusion? Okay, if not, then let's just move to next problem. Uh, Consider an electron initially is at is rest. If it start moving at velocity 10 to the power 7 centimeter per second, what is the approximate kinetic energy of such electron? So uh, that you just calculate by half mv square. So so yeah, so you can calculate energy as half of mv square, and the half of mass is 9.1 into 10 power minus 31 times b square, 10 to the power 7 centimeter per second square. So this will become 1.2 into 10 power 9.1 into 10 power minus 31 multiplied by 10 power 5 meter per second, and this will become 1.6 into 10 power minus 19 electron volt. So what is the kinetic energy? It will become, so this will roughly come at 10, it will get 28 point something 4 milli electron volt. So so then like the, see like the electron moving with this velocity will have energy corresponding to 28 milli electron volt, and with this level spacing we have only 1e minus 19 electron volt. So this electron has much higher energy compared to the level spacing, so it can jump to any other level actually. So this that helps that electron will be like we can assume this bands as a quasi continuous band in the part 4 actually. So this the answer will be answer closely matching will be around 28 milli electron volt. Other answers are wrong. So with this, let's move to next problem. So So yeah, so the consider an electron with energy of 1 electron volt impinging into the barrier height of 5 electron volt with a nanometer with a width zero point 0.5 nanometer. Assume uh, assuming tunneling probability in this case is T1. So how to calculate the tunneling probability? So basically, like if you consider quantum mechanical wave, so suppose we have a potential barrier. So suppose this is the 5 electron volt. So let's say this is thickness is A and this is the 5 electron volt barrier. Let's say call this as a V naught and the electron has a energy E. So now electron is moving in this direction. So let's just represent with different color. Yeah. So the electron has a energy is 1 electron volt, and let's assume for notation it's the E. So classically there is no probability of this electron moving to this side actually. But quantum mechanically, if this barrier is smaller, barrier thickness is smaller, there is a finite probability of finding electrons at the other side. So that is this phenomena is known as the tunneling actually. So lot of even chronic penny models and uh, others like description like are based on this. So to solve this kind of tunneling problems, basically what need to consider, you need to consider you need to solve the Schrodinger equation in three regions: first, second, and third. So here the potential is zero. Here the potential is 5 electron volt. Here the potential is again zero. So in the to solve the Schrodinger equation in this, so it is minus h bar square by 2m tau by tau x square plus Vx. This is known as the Hamiltonian actually. Applied on the wave function of the electron gives the energy eigenvalues. So this is the energy of the electron times psi x. This is known as the time independent Schrodinger equation. So in the region 1, basically this potential region 1 and uh, this is 0. So this you can assume as a 0. So the wave function will have the solution will have minus ikx time. Like the probability will be of the form of minus ikx, and this is the plane wave format solution. So in the region 1 and region 3, the electron will have plane wave like solutions. So here you can assume this as a plane wave. Here assume, so you can assume the plane wave. But in this in the second region, if you want to solve, then you need to solve basically so this will come at, so now this has a in the region second it has a finite potential. So you need to solve minus h square by twice m dou square by dou x square psi x, if you apply on this, plus v naught, the vx is constant. So basically v is independent of x. So you can write as a v naught times psi x equals to e times psi x. If you take this to other side, so you will reach as a dou by dou x square psi x equals to e minus v naught by so you can take this terms also, 2m by h bar square minus psi x. So this and you can this, because v naught is larger than e, so e is less than v, so you can get this term is negative. So this negative and negative sign become positive. So this 2m v naught minus e by h bar square, this you can represent as a gamma square times psi x. So this, if you try to find the solution of this equation, then you will find the psi of x is of the form of some constant c times exponential of minus gamma times x, and gamma is real function actually. Gamma is given by this. So if you take the probability, so basically the in this region actually electron the wave function will exponentially decay. So in this region it will become less, and after this it will behave like a plane. So if you take the probability, so this probability you take the mod of psi x is square. So this will become the form of minus 2 psi x. So this is basically the turning probability. So if you consider you need to so basically the x is the width of the barrier. So then in the two case you need to consider, once the uh, width is less and width is larger. So you will see when the width is less, the tunneling probability will be very high actually. So it will be around 10 times the tunneling probability. So the second case the distance is 2 nanometer, and the first case the distance is 0.5 nanometer. So it is approximately, if you take a1 by a2 ratio, so this is 0.5 by 2 nanometer. So this the a2 by a1 is around it's so it's 20 by 5, 20 by 5, and it is 4. So this ratio is around 4 times. So if you consider if you put all the equation, so e is given. So E is given, V naught is given, M naught, M you can take as the electron effective mass, H bar we know reduced Planck constant. Then you can calculate this gamma terms. Once you find this gamma term, then if you put in this equation, you can find the tunneling probability corresponding to this different wall conditions actually. So basically here you need to match, and here you need to match, and this is your tunneling probability. And if you want to compare, then you so if you want to take ratio of T1 by T2, so it will become E minus 2 gamma times x1 divided by E minus 2 gamma times x2. So this will become exponential of uh, uh, 2 gamma times x2 minus x1, and x2 is 4 times larger compared to this. So this term is positive. So this exponential term will be very high. So you can say that T1 will be much larger than T2. So the correct answer, so this is the positive. So the exponential will be exponentially increasing function. So then you can say like this the T1 tunneling probability is much higher compared to the T2. So the correct answer will be the third. So is there any confusion in this? Okay, so if there are no questions, let's move to next problem. Consider a particle in a 1D potential box of width L. Let E1 is the energy of the ground state and En is the energy of state with the quantum number n. What is the ratio of energy emitted when the particle makes transition from n equals to 3 to ground state and n equals to 5 to ground state? So basically we need to calculate ratio for delta E of 3 to 1 divided by delta E of 5 to 1. So we in the class the uh, particle in a 1D infinite potential well was solved, and in that the energy was energy of electron you can write as a h bar square k square by twice m, and k as you have a infinite potential wall, k does not take any value of moment k. So let me just give you more context. So, yeah, so in the case of free electron, k take continuous value, so all the values are possible. So E is basically h square k square by twice m. Once you confine a particle in the uh, periodic thing, this k will become discrete. Only discrete value of uh, k are allowed. So only integral multiple of k is integral multiple of pi by l, where l is this length of the potential well. Only integral value of pi by l are allowed. So these are pi by l. This is 2 pi by l. Spacing between these is pi by l. So only these are allowed. So then, like the particle will have, the electron will have only discrete energy are possible actually. So that we can calculate. So if we put in this, so E is basically h bar square n pi by l whole square by twice m. So it will become h bar square n square pi square by twice m l square. So now so this is E is a function of n actually. So this n is the number of which so it will has a different node. So how much number of this node will exist will define how much is the energy. So E from 3 to 1 will be equals to all the constant terms. Let's say call this C times 3 square minus 1 square. So all this other terms you can take as a constant. So these other terms, whatever the other terms are constant, then you can assume as a similarly E 5 to 1 is C times 5 square minus 1 square. If you take the ratio E31 by E51 will be equals to C will get constant will get cancelled. So it will become 3 minus 1 times 3 plus 1, it will become 5 minus 1 times 5 plus 1, which will become 2 multiplied by 4 divided by 4 multiplied by 6. So it will become 4 will become cancelled. So it will become 1 by 3. So the correct answer will be 1 by 3. So this is like the exact very few calculation you can get the answer. Is there any confusion up to here? Okay. So if there are no any doubts, then let's move to next problem. So yeah, so let's move to next problem. So can anyone tell? Let me. I have a question. So in the class we draw the in the class where we when we solve for chronic penny models and Venn diagram we calculated. So based on the chronic penny models, so this uh, sorry, yeah. So based on the chronic penny model and the particle in a box, you can you can assume periodic potential as this square potential well. You can roughly assume, you can approximate this Coulomb potential as the square potential, and what this periodicity is indeed. So like confining the electron leads to discrete nature, but when you take the periodic potential, what will have, it will lead to the jump in the discrete. So when you have so this is the uh, free electron uh, electron ek dispersion relation, and then when you have a particle in a box, then this will become discrete. This will become discrete. And when you take when you take multiple these wells connected together, then basically those wave function overlap, and you need, instead of single discrete level, you need to take consider the account of those overlap. So what those overlap does, it does create a gaps in this band. So at this at the at the this integral value of n pi by a plus b, if you consider this as a and this as a b, then n pi by a b, you will have a discrete jump actually. So this, because of this periodic potential, if you solve it, this will this energy level in betweens are not allowed actually. Those are not, as these known as the forbidden gaps actually. These are the forbidden gap. Those are not, those energies are not allowed. So when you make a periodic potential, so there exists a finite band of gap, not just discrete. So those are known as the forbidden band and lead to the formation of band. But since we are considering here only 1D case, so we can and this because of this discreteness, there is a periodicity in the momentum actually in the k space. So you can fold this band, you can shift this band to this side and this band to this side. So this will have the bands has 2 n pi by 2 pi by a plus b periodicity. So if you shift this band to this side, so you can represent this band structure in in the initial from minus pi by a plus b to pi by a plus b. This is known as the folded band structure or William Jones concept actually. But since this band diagram does represent a real 3D crystal, so what does it represent? So you see, like here, this the like around this, it is asymmetric. So basically, like because this symmetric is there, so you can only half of the band you can represent a full picture actually. So in the actual band diagram, so suppose the so if you have suppose the actual crystal, so actual crystal, so let's say FCC crystals are there. So you have this FCC or this kind of crystals is there. Then what will happen? So if you consider this crystal, so this so to fill this band, you need to move to the momentum space actually. So this 3D space crystal will have the 3D momentum space also. So here, because this is 1D chain we are considering, this has the only 1D crystal, but only in the case of 3D just Yeah. Yeah. So then, like this will have a different symmetry direction in kx, ky, kz. So this, like in the momentum space in the kx, ky, kz direction, it will look different actually. So these are those symmetric direction actually. So this k k K, gamma, and L values are those symmetric those symmetry if you consider, then like those different symmetry, then the band structure will appear like asymmetric actually. But this if you consider in one direction, so basically it's because it's symmetric, you can half only is required to represent a band. So in the same structure you can represent all the symmetries actually, all the branches and other things you can represent. So this was the little bit digressing for real understanding. So let's just move to the problem. So yeah, so the consider two symmetric band structure of silicon and gallium arsenide shown in figure. Silicon is an indirect band gap material and gallium arsenide is a direct band. So the band gap is, so let me define the band gap is the distance, like the minimum distance between the bottommost unoccupied band to the top, like bottommost unoccupied band. So this conduction band is partially occupied, or bottommost of the partially occupied band to the top of the partially unoccupied band. So basically, some electron from the valence band will move to different level, and this gap is known as uh, the the band gap. But in this case of two different materials, actually, for this case of silicon, you need to change this momentum actually. But uh, this vertical transition will lead to the emission of the photons, the zero rest mass. So this change is only possible if by considering the absorption and emission of the photon. Actual picture is comes in the actual scattering. If you solve for the perturbation theory and those kind of thing, then you can understand why this transition happened. But with this absorption of photon, this change of this the level will take place at the same momentum level. But in this case of the silicon, the on the x-axis also you need to change the momentum. So this is known as the indirect band gap material. But in case of gallium arsenide or other direct band gap material, no change of momentum is required. Delta K is not required. The top of the valence band lie in the top of the partially unoccupied band lie just below the top of the partially occupied band. So this does not, delta K is zero. So uh, that is known as the direct band gap semiconductor. So silicon is the indirect band gap, gallium arsenide is the direct band gap semiconductor. So S1 is correct. Silicon is indirect band gap, gallium arsenide is indirect band gap. So this is wrong. So silicon is indirect, and this second one is wrong. In a direct band gap material, the momentum is conserved by when the electron makes transition. So this photon can provide this large change in momentum. This has to be provided by some some modes or some phonons vibrations or some vibration corresponding to the atoms or nuclei actually. So this change in momentum is provided by those phonons, which are the vibrations of your atoms. In a direct band gap semiconductor, momentum is conserved by when a electron make a transition between band, and in indirect band it is conserved by simultaneous absorption and emission of photons. Yeah, so this is correct. So basically, in direct band gap momentum is conserved by just change in the transition of the energy, and indirect game or emission of the photons, and the indirect game, this transition as well as this transition is required. So absorption of photon plus phonons is, so horizontal is phonon, vertical is photons, so both are required for this transition actually. So S3 is uh, correct. But since like the photon, like if you take a normal photons, that does not have, as we calculate the momentum corresponding to or momentum corresponding to the photon, that is very small compared to the matter wavelength and the corresponding momentum. So the photons can't provide that much large change in the momentum. So that this absorption like the emission, like the moment of this, the electron transition from conduction band to valence band is very likely. It does not mean that it does not happen. It happens the phonon mediated process, but that is the probability of that emission is very less, so that is very inefficient emission. So we can assume that that does not happen at all. So the recombination is less efficient. So let's go to the fourth option. In an indirect band gap semiconductor, momentum is conserved by the photon emission and in a direct semiconductor, and in which conserved by the word phonon and uh, in an indirect semiconductor, the momentum is conserved by the photon emission, and in a direct semiconductor, it is conserved by the phonon and photon emission. No, it is reverse actually. In direct, it's conserved by the photon emission, and in indirect, it's both phonon and photon. So this option fourth is wrong. Recombination is much more efficient in gallium nitride than silicon, hence used an electrode. Yeah, so as we have discussed that gallium arsenide has a much more effective recombination compared to the indirect band gap silicon semiconductor. So S5 is the correct. So the other option is just reverse, that is wrong. So the correct option is S1, S3, and S5. So yeah, so this is the correct answer. So if you have any confusion, that you can ask. Okay, so let's go to let's move to next problem if there is no confusion. So the cutoff wavelength of light can be used for intrinsic excitation of semiconductor material. So basically, if you shine a light, so suppose this the electrons are here, so this is unoccupied, so the holes are here and electrons are there. So if you take, then this holes will emit the electrons will excite to higher energy levels, and here it will be a hole will be created, and it will lead to absorption of this. So this minimum absorption is this minimum band gap actually. So the cutoff wavelength is defined by the minimum absorption actually, and minimum energy of the absorption, and that is your band gap actually. So Eg is basically hc by lambda c. So lambda c you can calculate hc by eg, and eg hc, this shortcut you can take 1.25 electron volt divided by eg in electron volt. So then you can calculate 1.124 divided by 1.1 electron volt, and this lambda is in micrometer. So this will come around 1.1 something. Yeah. So this the correct answer is approximately 1.1 electron volt. The correct answer will be B. Okay. This was fairly straightforward. In 10 year before in the gate EC, this question was asked, and like you can see, like this semiconductor that time it was quite easy, but now like it's quite hard questions are asked in especially those electronic device. The exam pattern has moved quite a significantly in last 10 years. So this problem was 2 marks, but nowadays you don't expect this problem in. I don't think it will be there for even 1 mark actually. So okay, so I think uh, if you have any doubt, you can. Yeah, yeah. Hi, Sanjeev. Yeah, sorry. Yeah, it will be available. So in your interface in your account, it will available as a live session. In that, I think one Excel sheet will be there. In that, you can find the session corresponding to this session. Actually, all the slides, whatever scribe I have used, and the video record, the screen recording of this session will be available. I will just upload on YouTube just in a few minutes. Oh, okay, fine. Thank you. If you have any doubt, any things, you can ask, or like if you can go through this material, you can ask in next session. Like before starting the next session, I will take I will take a doubt session before even today's class, or whatever the content covered in the next week problems. So yeah, so be be like don't worry about like if your like English is not good. I can talk in Hindi also, so no worry about that thing actually. So I can understand fairly good in Hindi. So if you have like hesitancy in speaking English, then you can ask in like whatever language suits. I can understand English and Hindi. So even if you can like barely if you have hesitancy speaking, then you can write in the chat box and then I can reply correspondingly. So then I hope you enjoy this session. So thank you so much for patiently listening this session. Then today my internet was a bit hiccup, so sorry for those disturbance, and I will take care. Maybe fix those things in next session. I hope it will be smooth. And yeah, so we till the time keep enjoy learning. I hope you will be doing good. So thank you so much for listening this session. We will meet same time at the next week. So I hope till then, bye. Have a nice time. Goodbye. Good night. Okay. Okay. Same to you. Thank you. Bye.